the last part of part B, B.4, optimality of algorithms. All right, first, let's look at the new problem we want to solve. Find the minimum of an array. The problem, given an array. Here, we do not mention ordered or unordered. If we do not say anything, we mean unordered. Find the index I such that A of I is the minimum of the array. Yeah, so the problem is very easy. So I think you can easily solve it. But here we have another important problem to discuss. All right. First, the problem type. This is another basic type problem in our algorithms. We call a selection problem. So what is the selection problem? First, let me give you the definition of this type of problems. Find the kth smallest element given a positive integer k, positive, k greater than 0, positive integer k. We want to find the kth smallest element in a given array. That's simple, all right? Yeah. So for the minimum problem, that's easy. It's a special case of the selection problem, k equals 1. For the maximum, what's the maximum? The maximum problem, k equals n. For the median, yeah, find the median. You know the median, right? The element in the middle, but sometimes people ask, what do you mean in the middle? Because there are even number of elements or odd number of elements in an array. Yeah. So in that case, we define, for the median case, floor function, n over 2. That's what we mean in the middle. Yeah. So more specifically, we can call it a left median, right? Because sometimes you may have left median or right median when you have what? Even number of elements, right? Yeah. Left median, right median. Yeah. All right. Here I give you the reference in the textbook, so you can study those pages. Now let's solve it first. To solve this problem, pretty easy. Yeah. Analysis also pretty easy. Yeah. But our main focus is the discussion after that. After we get a solution, then we have a lot of discussion about this problem. All right, the solution, we scan the array once from beginning to end, but when we start, we initialize our variable min. So we create a variable called min to store the minimum value. At the beginning, we just store the value of the first element as our initialization step. After that, we do the general step. The general step, we compare the main variable with the current element, A of I, that is the current element. So we want to compare which one has larger, smaller, including that equal case. Yeah. So we consider these two cases. The first case, the main value is greater than the current value. That means the current element value is smaller than the main variable value. So we can get a new, smaller minimum value. So we update the main value variable by the value of the current element. So we make it the current minimum in the main variable smaller. Yeah. We'll keep doing this. Every time when we do update, we make that value smaller. All right. Otherwise, if we don't have that condition, we go to the next iteration. Okay, yeah, so we set iterations like this. So compare main with a of I plus 1. Yeah. Keep doing iterations like that. When we do the comparison, we check the value and make our decision like that. Yeah. Until we reach the last element, I equals n minus 1. That's the last one. After we do iterations on also all the possible comparisons, at the end, we get the minimum stored in this main variable and we return its value as our solution. Yeah. Return the main, let me see. Find index I, right? Yeah, actually we should return and I. Yeah. To be more complete, we should return both I and the main. How about that? I and the main, both. Yeah. We want to know the position in the array that has the minimum value, but also we like to have the minimum value. Yeah. So based on the requirement of the problem. Yeah. So here, we may because here after you return index I, the main just equals a of I, right? So we can get that easily. Yeah. All right. Then let's look at the analysis, the number of comparisons we need to solve this problem. Can you tell me what is the exact number of comparisons? Sometimes we use approximate number, sometimes we use exact number. This place, I want to ask you the exact number of comparisons. Some of you may give me n, but that's not very precise. The precise number is n minus 1, not n. Why? Because for the first element, we don't need a comparison. The first element is our initialization step, so no comparison. Okay. After that, for each remaining element from 1, a of 1, a of 2, each one we need one comparison. So for the whole array, we need n minus 1 comparison. Okay. Now we finish solution and analysis. Next, discussion. For our discussion, we ask this question. That's the common question we ask when we solve an algorithm problem. Is it possible to further improve the algorithm? Right? We want to see if we can improve this algorithm or not. Is this the best one we can get? That's important. Yeah. All right. Usually for the question like this, we have two options in our decisions. Yeah. All right. The first option, we improve the algorithm. Try our best to improve the algorithm. That's the first way we can do. The second way, because the first way, if you try many, many times, you may not be successful. In that situation, you need to consider the second option. Convince people it is already optimal. Our current algorithm is already optimal. That means nobody can further improve it. Why you spend time? Why you waste your time to do the improvement? For this video, this topic, I want to focus on the second option. Yeah. All right, so let's look at that. The second option, to do that, pretty hard. Why it is so hard? So usually it is pretty hard. Okay. Why? Because we need to do something like this. Okay. We need to convince people among all the possible algorithms to solve this particular problem. Here, the minimum problem. This one is the optimal. How do you show that? This one is optimal. The hard part is, how do you get this part? All the possible algorithms. That's hard. How do you exhaust all the possible algorithms? Nobody can exhaust it. All the possible algorithms to find the minimum. So nobody can exhaust all the possible algorithms, especially including unknown algorithms. There are some algorithms still unknown. Nobody has discovered that algorithm, unknown algorithm. How can you exhaust those algorithms, including unknown algorithms? That's hard. Yeah. So the next question is it possible to study unknown algorithms? It looks like, if you use some straightforward logic, it looks like it's impossible to study unknown algorithms, right? Straightforward logic. But if you think it deeply, then you may have different answer. The answer could be, it is possible to study unknown algorithms. Even unknown, we can still study. Why? Because we can catch some critical property. This property can cover all the algorithms that solve this particular problem, including unknown algorithms. Even we don't know those algorithms, the details of those algorithms, but we find some property that can cover those unknown algorithms. It's like that. Okay? So in our next slide, we will see it. We can find that property that cover all algorithms for the minimum problem. All right. In this slide, we will answer this question. How do we convince people that our algorithm is optimal? Not very hard, not very long. If we get that critical point, critical property, we can do that. All right. Let's do it. Here, I'd like to point out some real-world experience we can use, we can borrow. So we can do the logical reasoning using analogy. So this experience, everyone has it. So we are familiar with the environment for this special situation. All right. When we solve our minimum problem, we need to do comparisons, right? Then I use another event that is similar to comparison to do the analogy. So what's that? Match. Sports match. Play games in sports. So two players or many players, they need to play matches among them, right? Okay. So let's consider a match between two players. You can see the situation similar to comparison. Why? So let's look at that. When we do comparison, we have these things: less than, okay, equal, greater than. We have three cases. Yeah. But when we play a match, we also have the similar situation. So less than, here for our current minimum problem, we want to make it correspond to when. So when one number is less than another number, for example, when A less than B, we call A is the winner. The reason is simple, because we want to make the final winner the minimum. If you use this rule, then the final winner will be the minimum. That's our goal. Yeah, so that's why we make it less than equivalent to the when state. Yeah. If you want to find the maximum, then you can make it greater than as the when state. All right. Equal, that's the tie case, tie state. Greater than, that's the lose state. Okay. If you do that kind of analogy, then we can make our convincing argument for the optimality of our algorithm. Yeah. All right, so now I try to make the convincing argument. Yeah. So you can see if it is a strong, convincing argument from your understanding. All right, so I do it one by one. Okay, all right. The first statement. Yeah, so we did that before. Imagine the mean value is the final winner. Yeah. So we talked about that already. Yeah. Then, to get the winner, it needs to beat all the other elements in the array. Okay? Yeah. Through comparisons. The key meaning here is directly or indirectly. Directly, it's easy. Yeah. A beats B. Yeah, that's easy. But there is a situation one player beats another player indirectly, not directly. Yeah. Here, let me give you a simple example. Yeah. Suppose we have this. A less than B. So A beats B. B less than C. B beats C. Yeah. Then we can conclude A beats C. Right? Do we need another match between A and C? We don't need, because A beats C indirectly through transitivity, because our inequality in our rules based on the transitivity property for unequal, less than, here, less than, A less than C, and A beats C. So this case, indirectly, we include it. Yeah. Because if we do this way, we can minimize the number of comparisons. We don't want to waste number of comparisons. Yeah. All right. Next statement. If an element loses once, it is eliminated. It cannot be the final winner, right? That's obvious. The final winner never loses. during the whole tournament. Let's assume there is a tournament. Okay, the final winner cannot lose. Okay, all right. Next statement. Each comparison can only eliminate one element. One comparison, one match. Okay, one match between two players, the result can only eliminate the loser. The winner cannot be eliminated, right? How can you eliminate the winner? So that's ridiculous. So this one, based on our real-world experience, can only eliminate one element. No problem. All right, next one. In order to get a final winner, that winner needs to eliminate n-1 elements directly or indirectly. Indirectly is fine, but eventually the final winner should eliminate all the remaining n-1 elements. Okay? Now our conclusion. Because one match can only eliminate one player, in order to eliminate n-1 players, you need to play at least n-1 matches. Here we need to do at least n-1 comparisons. You may need to do more, but you cannot do less than that number. Yeah. So this is the critical statement. Okay? So if you have no problem understand this statement, then our last statement of this argument. Why our current solution is optimal? Because our current solution needs exact n-1 comparison. That's the minimum. Yeah. Because based on our previous argument, statement, any algorithm, no matter known or unknown, it needs at least n-1 comparisons. Yep, that is true. Yeah, based on our logical reasoning from beginning to end, that's true. Yeah, but our current algorithm reaches that performance. That's why our current algorithm is optimal. That's the convincing argument. Okay. All right. Yeah. To summarize the whole thing, so we complete this topic, but at the end, I want to mention the most important method we used in this problem, elimination method. Yeah. Why we can get this optimal solution? Because here we use the elimination method. Okay. Try to eliminate as many as possible elements. That's the elimination method. Yeah. Here it looks like so simple, but later we will use this method many, many times. And sometimes we use it to solve some very difficult problems. If you do not use the elimination method, it could be very, very hard. But if we use the elimination method, we reduce the number of elements in the consideration. The faster we reduce the size of the problem, the quicker we can solve the problem. Okay? All right, so we finish class for part B.